In this lecture, we're looking at Diels-Alder chemistry. We'll go over a couple examples that highlight some features of the reaction, and then incorporate Diels-Alder reactions into some multi-step synthesis problems. In a Diels-Alder reaction, you've got to have a 1,3 diene, and that will function as your diene for the reaction. And that diene must be able to adopt an S-cis conformation. So many times it won't be drawn in that S-cis conformation, but as long as it's not a cyclic structure or has some other barrier that keeps it from being able to adopt that conformation, then typically they'll undergo Diels-Alder chemistry. And we'll see an example of a problem drawn that way. This diene is in the S-cis conformation because the two double bonds are angled in the same general direction. Some other information here about the Diels-Alder reaction: electron donors will activate dienes. And here we're talking about substituents. In this case, we don't have anything bonded to our diene. If we look at the other part, a simple alkene, in this case, that's the dienophile, and it can react with the diene. For the dienophile, electron withdrawing groups activate the dienophile, and essentially what that means is that it will react at lower temperatures and faster. Here's some examples. A simplified chart of electron donating substituents and electron withdrawing substituents. Donors are going to be any kind of alkyl group, or if an oxygen is directly bonded to your diene, for example, that oxygen could be bonded to an alkyl group. It could be a hydrogen, or this could be a carbonyl here, as in an ester. But as long as the oxygen is bonded to the diene with its lone pairs of electrons, it's actually a potent electron donor. And the same goes for nitrogen. This could be an amine nitrogen, or it could be part of an amide. As long as the nitrogen is bonded to the diene, that's a donating substituent. For electron withdrawing groups, halogens, or anytime you have a carbon that's not just an alkyl group, but a carbonyl carbon for a ketone or an aldehyde, or for a carboxylic acid. And typically this is the abbreviation for aldehydes. So all of these carbons are carbonyls. And also for an ester, if it's the carbonyl carbon bonded to your diene or dienophile, then that would be an electron withdrawing group. Similar, the cyano group. And then a nitro group is a potent withdrawing group, because this nitrogen does not have a lone pair of electrons. It's actually formally positively charged. In the Diels-Alder reaction, the diene and the dienophile will react to form two new carbon-carbon bonds, and that gives you a 6-membered ring. And there'll always be one pi bond remaining. In this case, it's just cyclohexene, since there were no substituents. To draw the mechanism, you normally want to line things up appropriately to make it make sense. And so we'll line up our diene and dienophile, ready to form a 6-membered ring. We can see the pi bonds rearranging to form two new sigma bonds in the product. Now we can apply this mechanism to some more complicated examples. So here's one, and you should go ahead and attempt it and think of how it would work. Identify your diene and your dienophile. In this case, the diene is drawn over the arrow, but it can still react. It's drawn in the S-trans conformation, but with a little bit of energy, a little bit warmer than room temperature, it's easy to convert this in the reaction into the S-cis conformation. And so there's nothing preventing it from adopting that conformation. And so we can draw these two in conformations that allow them to react. The part of our dienophile that's going to react is that carbon-carbon bond. This dienophile is actually a typical dienophile for Diels-Alder reactions. Notice how the alkene is bonded to two carbonyl carbons. So each one of those carbonyl carbons acts as an electron withdrawing group, and so it's a strongly activated dienophile. With heat in this reaction, just like any Diels-Alder reaction, will form a six-membered ring, a cyclohexene. The substituents here, since they were cis in the dienophile, because it's part of a cyclic, will be cis in the product. And you can always count your carbons to verify, but we had 1, 2 carbons plus 4 carbons. We've only got 6. 6 carbons in the structure of the cyclic alkene, and then the 2 carbonyl carbons as part of this other functional group right here, cis to one another. This is a meso compound, and so we won't get a mixture of enantiomers. Here's another example to try. In this particular case, our diene is written over here, rotated in such a way that's not convenient for predicting the product, and our dienophile is up here, a trans conformation. And so we can set this up to react. Again, the mechanism for these is all the same. I can fill in the one we did previously. Down here, when we have a cyclic diene, the product gets a little complicated, but the mechanism's still represented in the same way. Now we're forming bonds between these 2 carbons and these 2 carbons of the dienophile and the diene. This is going to make a bicyclic system. It's still a 6-carbon ring with a double bond in it, so a cyclohexene, but now it's bridged by a single carbon, and that bridgehead carbon is the 5th carbon of the diene that was sp3 hybridized. To handle these substituents, and these are electron withdrawing substituents, so they've activated the dienophile. Since they're trans in the dienophile, they'll be trans in the product. And so we can get this particular structure, or it's an enantiomer. But in either case, the groups must be trans. Now we can look at two cyclic systems reacting and try and predict these products. Taking into account what you know about this particular bicyclic system. We can start drawing our six-membered ring in this fashion with a bridgehead carbon. And so we'll have the double bond here. And then, since these two carbons of the dienophile are going to be these two carbons of the bicyclic system, we can see what else was bonded there. Because it's part of a ring, it's bonded in a cis-like fashion. But with a bicyclic system here, there's a difference between both groups angled upwards or out as a wedge, or angled downwards or back as a dash. In the case of reactions of cyclopentadiene, it always favors the endo product, or where these are dashed lines. And so this is a carbon-carbon bond to those carbonyl carbons. It can be represented like such. And again, this is the endo product, and this is what's exclusively observed in this reaction. So you get essentially 100% endo. And you get 0 of the exo. And this is typical for reactions of cyclopentadiene. Now we're going to look at some multi-step reactions that utilize Diels-Alder chemistry. This one can get us started. Try to figure out how you would go from 1,3-butadiene to our cyclohexadiene product. It's going to take 2 or more steps to do this. So work on a solution. This will involve reactions from recent chapters and will involve a reaction from several chapters previous. The key is that we need to form 2 alkenes. Well, when you look at 1,3-butadiene, and this is drawn in the S-trans conformation, but it can adopt an S-cis conformation, so it can perform a Diels-Alder reaction. And so it'd be nice if we could simply just react with 2-carbon ethylene in a Diels-Alder reaction to get the final product, but we get something very similar, cyclohexene. So we're missing a pi bond. Well, how can we put a pi bond here? In one step, it's not achievable. But we know reactions that involve alkenes that can get us there. One reaction that's recent is allylic halogenation. In this case, there's only one single product that you can get, even though that radical could be at 2 different carbons, because they turn out to be identical radicals. and we obtain this as a racemic mixture. Perhaps it'd be clearer. Let's go ahead. Now from this product, where we have another high-yielding reaction, in one step, we can form this other alkene by simply using a strong base. One of the best bases for an E2 type reaction is potassium T-butoxide. And this will be an E2 reaction. But it's a classic method to go from an alkyl halide to an alkene. In this case, the conjugated system is favored because it's so much more stable to have conjugated double bonds. The only other possibility would be to form a double bond between these two carbons. That would give you sp hybridization on this carbon, which is prevented by the six-membered ring, but that would be much less stable anyway than a conjugated system we have here. So these are good reactions to know. This one's much more complicated. And the purpose of this multi-step synthesis probably isn't to discover the ultimate best synthesis of this compound, but it will be the best synthesis based on what we know already. It's more to review as much as we can from the current material, as well as incorporate reactions from the past that are still important that we should know. Count your carbons, you've got a 4-carbon chain and another 4-carbon chain. So initially you think, well, this one's not going to involve Diels-Alder chemistry because we're not adding carbons. Recently we've learned 2 different ways to make ketones through oxidation chemistry. You can oxidize alcohols to form ketones and aldehydes. So potentially, if we had a 1,3-diol, we could oxidize that with PCC at both sites to give us an aldehyde and a ketone. So that's one thought of how to get there. The other way we recently learned how to make aldehydes and or ketones was through ozonolysis. As a hint, think of a molecule that could make this as an exclusive product using ozonolysis. It want to be symmetrical. So if we have this cyclohexadiene where the bonds are not conjugated, then this will work to form this through ozonolysis. And these are alkenes, so we'll use DMS in the second workup step. So that cleaves the bonds, and they end up producing the same ketone aldehyde molecule. And so now, as part of this problem, thinking not only of how we can go from this structure to this, let's say we can only use 1,3-butadiene as the source of all of our carbon atoms throughout the synthesis. But we need to think about what we could react with this to make this molecule. What would our 1,3-butadiene react with to make this particular one? Keeping in mind there's that other pi bond in the structure. Well, you'll need an alkyne. And so 2-butyne can react with 1,3-butadiene to make this dialkene. And so the mechanism for that is the same as we've seen before. Since we are only reacting with one of the alkyne pi bonds, you end up with one left over. And so these two, the mechanism is shown here for production of this product. So that's a way to use butadiene. So the other part of this synthesis problem becomes, how can you get from here to here? Well, we know we can make alkynes from other alkynes, but if we know we're starting with a 4-carbon piece, we're not going to grow this from a smaller alkyne, most likely, but we can make it from a dibromide. And we can worry about the stereochemistry later, but a dibromide can react with 2 equivalents of a strong base, like sodium amide, to do a double elimination reaction producing the alkyne. So now we have to think, how can we get from butadiene to a dibromo species? Well, we can take advantage of conjugate addition, and if we react at HBr at low temperature, so cold, that'll favor what kind of product? That's the kinetic product. And so at cold temperatures, you'll get the product that had the more stable carbocation as its origin. So if the carbocation was at this, it'd be a secondary allylic. And so that's one way to go about the business. To react this compound to make our dibromo, essentially you could just keep the reaction in HBr under cold conditions. Once we've formed this initial 1,2 product, the kinetic product, if we had more HBr available, then that could react here in classic Markarnikov fashion to put the bromine on the more substituted carbon. In this first product, we'd have a mixture of enantiomers. For the second addition, you'd get also a mixture of all the possible enantiomers and diastereomers. And so down here, you would have all of 4 possibilities. Now, all 4 of those possibilities can react with 2 equivalents of strong base to make our alkyne, so it would not be a problem. You wouldn't have to separate them. But so this reaction essentially goes back to the alkenes chapter, and it's just Markarnikov addition. If you ran it at a much higher temperature with HBr, then you would get the thermodynamic product. And so this would be the more stable double bond, the internal alkene. And so this looks like a problem because you don't want that bromine on the external site. However, the alkene being on the internal portion is a good thing for making 2 bromines there. We just have to get rid of that bromine. If only we knew a way to replace a bromine with a hydrogen. Well, from the reductions chapter, we do. And so lithium aluminum hydride does not reduce alkenes, but it does reduce carbon halogen bonds and replaces it with a hydrogen. And so we have this alkene. Now we can specifically make the trans product with just a bromination reaction. So regardless of how you set up the first reaction, it's still achievable to get to the dibromo. We eliminate to form our alkyne. And that alkyne can react with our butadiene that we started with in the first place, and then we undergo ozonolysis to complete this reaction. So there's probably other pathways. I wanted to involve as much recent chemistry as possible. Probably this kinetic pathway would be easiest because you could start cold and then just add in more HBr, have it there present to begin with, to end up with this product that would do your reaction.